Hey guys, so this is the last lesson out of kinematics. It's called advanced projectiles. Now the projectiles themselves aren't any more advanced. It's the same kind of problems that we've been looking at, but there are, I guess there are two here, I guess, that are kind of a little bit more advanced. But what we're going to do is we're going to look at what happens if we don't have values for these things. So we've got a v and a theta. I don't know what v is. I don't know what theta is. We're going to solve this problem here in general. We're going to come up with some very, actually quite interesting results. Now, it requires a little bit of mathematics that some of you may or may not have, depending on what grade you're in. If you're in grade 11, you may not have seen what we're about to do, and that's okay. Just buckle up for the ride and kind of enjoy the results at the end. So we're going to use the setup here as it is to find an algebraic expression for the flight time and the range. And when we get these results, we're actually going to add them to the formula sheet. So it's level. We got level ground. We've got a Vx component, Vx initial, and we're going to have a Vy initial. We don't necessarily know what those are. Yeah, we're going to break it up into horizontal. We're going to break it up into vertical. Horizontal and vertical components. Horizontally, I've got a Vxi, and that's going to be equal to V cos theta. And a Vyi is going to equal V sine theta. That's all we got. And we've got an AX. As far as the velocities go, that's it, because we don't have values for V or theta. AX is equals 0 meters per second squared, and Y equals 8 meters per second squared. Let's see what we can do here. We want the flight time. So we can just go, because this is level, we can just go from beginning to end. It's relatively straightforward. Oh, actually, no, I lied. For the result that we want, we're going to break it into top and bottom. And we're going to come up with an interesting result here that we can just double. So I want to find the time to the top, T top. So T top is going to be found using, at the top, we know that Vy top equals 0. So Vf equals, we can use this kinematic equation, Vf equals Vi plus At. Vf is 0. Vi is V sine theta minus 9.8 T. So we're going to get that T is equal to, we're subtract my V sine theta over, and then we're going to divide it by negative 9.8, giving us V sine theta. Because they're both negative, the negatives cancel. And this is the time to get to the top. Because this thing's level, we know that T total equals 2 times T top. And so that's just going to give us this expression here, 2V sine theta over 9.8. And this is true over level ground. Which is a nice little result. We like this. So we're going to put a nice little box around it. And in a second, we're going to add it to our formula sheet here. What are we going to do next? We are going to find the range. So that's the total time. Let's find the range. So the T total, I'm just going to put the expression over here, is equal to 2V sine theta over 9.8. So the range we want to find, so it's going to be a D equals VT. So D is going to equal, and now it's my Vx initial, so that's V, I'll just put it in here, Vx initial times T total. You know, we've got these two different expressions here. Vx is V cos theta. And time is times 2 V sine theta over 9.8. Now we can do some rearranging here. Sorry, I'm going to, yeah, I'm just going to go this way. I'm just going to put a little box here. Just to break those off. So we're going to get, do some rearranging. We're going to get v squared 2 sine theta cos theta over 9.8. Now there should be a relationship here that those of you who have taken pre-calc 12 have seen. 2 sine theta cos theta is a trig identity. This trig identity happens to be equal to sine 2 theta. So we're going to get v squared sine 2 theta all over 9.8. And this is the formula. So we're going to box. For the range over level ground. Which is really quite cool. Now, you know what? Let's add those to our formula sheet as it's right now. Let's do it. So I've got these guys here. This is for a projectile over level ground. Okay, these results are true for any projectile over level ground. We've got total time, or t total, we'll write it like that, equals 2v sine theta over 9.8. And the range is v squared sine 2 theta also over 9.8. You are welcome to use these results should they prove useful to you at any point in the future. This gives us an interesting result here, though. We can look at what angle should we launch a projectile so as to retain a maximum range. Now, again, if you haven't taken pre-calc 12, this is not going to make a lot of sense to you. But here we go. Buckle up. The maximum range, it means we want to maximize v squared sine 2 theta over 9.8. If we want to maximize this expression, let's look at what we can actually do. To maximize this, assuming our velocity is standard, is constant, and that 9.8 is not going to change because that's the acceleration due to gravity on Earth. What that means is we want to maximize sine of 2 theta. Well, what do we know? Based on the math, the trig you looked at pre-calc 12, we know that sine is a maximum at 90 degrees. So sine of 2 theta is going to be a max at 90 degrees. So if you want 2 theta equals 90 degrees, divide by 2, divide by 2, we are going to maximize this thing at theta equals 45 degrees. So at what angle should we launch a projectile so as to attain a maximum range? 45 degrees, which is useful information if you want to, bomb someone really far away. You want to maximize the range of your gun, for example. Flip the page. Cool results. I was gonna have a kind of a hand wavy conversation here. The algebra from example 1 can be used to show that the range is symmetrical around 45 degrees. What that means is this. If I have 45 degrees, this is going to give me a maximum range. but it's symmetrical around 45. Means if I go up 15 or down 15, I'm actually going to get the same range. And what the reason for that is this. Well, let's take a look at this. Boom, boom, boom. Lands right there. Let's look at the 60 here. Okay, this is what's going to end up happening. In this bottom one, Vx is much, much larger. If we look here, actually, no, I should be using green for this bottom one. I've got Vx, and I've got Vy. Now, my Vy is small relative to these other two. My Vx is much, much larger. So what this is going to be is, this is going to be a very fast projectile. It's going to make its way over here very, very quickly, and it's not going to rise or fall very far. The Vy is not very big. Total time is not going to be very long for this one. For this one, though, I've got a Vx that's a lot smaller, but I've got a Vy that's a lot larger. So total time here, T total, is larger. Because my Vy is really, really big, it's going to go way, way, way up high, and then it's going to come back down. But either way, we've got the same range. And so what that means is this. There's some practical results for this. If you're in the military, for example, and you've got a target and you know what the range is to that target, you can shoot low and fast, or you can shoot high and slow. It depends on a few things. It depends on the speed. Is your target stationary? Is your target moving? Are there objects in the way that you have to avoid? There are, based on this idea that a maximum range is at 45, and that because it's sine, and sine is symmetrical, if you've seen the graphs of sine in pre-calc 12, you'll know that on either side of 90, the graph is symmetrical. And so you've got options, practical options, when you're looking at the physics of this kind of thing, for hitting different ranges. You can aim your gun really, really low, get a very, very quick hit, or if you need to avoid obstacles, up and over is going to do the job as well. And it all depends on how these Vx's and Vy's, or it all occurs because these Vx's and Vy's change in relation to each other. Cool results. Again, if you haven't taken pre-calc 12, this is not going to mean a lot to you. Just nod and smile and say, yes, this is a cool result. And then we move on. I am, should I do this example for you? Why not? Let's take a look at example 4 here. Just to show you kind of what these kinds of questions look like. Calculate the vector velocity and the vector displacement of this projectile. Now we're just putting some stuff together. It's a slightly more advanced question. Again, we're not going all the way to the bottom. We are trying to figure out at 3.5 seconds how fast, total velocity, and the vector displacement for this object. Actually, you know what? No, we're gonna ignore the vector displacement. Ignore the displacement. We're just going to find the speed of the object at 3.5 seconds. Now let's draw this thing. I've got a Vx initial, and I've got a Vy initial. I've got a horizontal, and I've got vertical components. I've got Ax, I've got Ay, I've got Vx initial, I've got Vy initial. Ax is 0 meters per second squared. That's negative 9.8 meters per second squared. My Vy initial is 20 sine 50. This is going to be 20 cos 50, which is going to give us, that's 12.86. meters per second, and my Vy initial is going to be 20 sine 50 is 15.32 meters per second, and we actually know the time. T equals 3.5 seconds. T equals 3.5 seconds. So somewhere in space. We've got, I want to know V equals question mark, and I want total V. So let's take a look at what we've got here. I can find V final. V final in the Y direction. That's what I'm looking for. So we're going to use VF equals VI plus AT. So VI is 15.32 minus 9.8 times 3.5. We're going to get a VY final of 15.32 minus 9.8 times 3.5. That is negative 18.98. So we actually know that this object's on the way down already. Meters per second. And we know that Vx initial doesn't, or Vx final is the same as Vx initial because that doesn't change. So what that means is this. We've got an object here that at 3.5 seconds has a velocity this way of 12.86 meters per second and a velocity this way of negative 18.98 meters per second. So that's the total velocity that we want right there. And that's just going to equal the square root of 12.86 squared plus negative 18.98 in brackets squared. It matters, the brackets matter. I see mistakes like this all the time, and by physics 12, we've all taken pre-calc 12, brackets shouldn't be an issue. I'm going to get a velocity of 12.86 square root of my answer. It's going to give us a velocity of 22.93 meters per second, and I need that angle in there. Theta is going to equal the tan inverse opposite over adjacent. That's going to give us an angle of tan inverse of 18.98 over 12.86. That's 55.88 degrees. So we're going to quote this by saying our velocity is 22.93 meters per second, 55.88 degrees. Now, it doesn't make any sense to talk about north, south, east, west in a problem like this, because this is up and down, this is left and right. So the way you quote this is by saying that our direction is 55.88 degrees below the horizontal. And that's the kind of question that would likely show up on a kinematics test near the end on a written section, asking you to find the total velocity of a projectile in flight. There it is. Flip the page. There's one more example, I think. Yeah, one more example we're going to do. We're going to do example 7. Before we get there, we're going to kind of have a hand-wavy conversation about example 6. We're not going to do 5. Let's do this guy here. Let's say while playing paintball, Peter spots Tom in a tree. Peter aims straight for Tom and fires. Tom sees this, and the instant Peter shoots, Tom lets go of the branch and begins to fall, hoping to avoid Peter's shot. Was this a good idea? Now, the key here is that, again, we'd have a conversation if you were in class, but you're not, so I'll just kind of tell you. The key here is that Peter aims straight for Tom and fires. What's going to happen to the projectiles as soon as it leaves the barrel of that paintball gun? It's going to start to drop. And so the trajectory of the paintball isn't going to be a straight line. It's actually going to start, to fall right away. So because Peter's aiming straight for Tom, that bullet's actually going to miss Tom. It's either going to hit lower on Tom or it's going to drop beneath Tom. So is it a good idea for Tom to fall? Well, no. At the very least, he should hang on to it. It might hit lower on the body. But if he's going to drop the instant this shot gets fired, he's likely going to take the shot as he falls because the paintball itself is going to start to drop as soon as it leaves the barrel of the gun. No. It wasn't. Period. Flip the page. One more example. Look at something looks like this. A basketball is projected at an angle of 30 degrees if we want the ball to go into the basket 5 meters away horizontally and 2.5 meters upwards vertically. At what speed should we shoot? This is not, oh, sorry, I should move this over. This is obviously not something you're not going to sit on a basketball. Yeah, I need this kind of speed, but, and you have no way really of controlling your shot with that level of accuracy. But these are the kinds of decisions that your brain is constantly calculating and adjusting for in a sport like this all the time, whether the numbers are concrete or you're estimating them. This is what's going on. This is a cool problem to look at here. So we've got a basketball being thrown. We're looking for V. So there's going to be a Vx initial and a Vy initial. We want the basketball to go in the hoop. How do we do this? So we set this problem up exactly the same way that we've done all these other ones. We've got a horizontal set of components, and we've got a vertical set of components. I've got an acceleration in the x direction, which is 0 meters per second squared. I've got an acceleration in the y direction, which is negative 9.8 meters per second squared. And in this particular question, I've got a Vx initial, but I don't know what it is, so we're going to call it V cos 30. We do know the angle in here is 30 degrees. And this is going to be Vy initial is going to be V sine 30. I do know my range, my horizontal range is 5 meters. And my vertical displacement is positive 2.5 meters. So let's see what we can do here. We don't know there's a few things we don't know. We don't know time. Now, normally what we would do is if we had a bunch of information, if we had V, we'd go through, we'd find the time vertically, and then we'd go back and we'd look at the horizontal. But because we don't know velocity, we actually have to go completely backwards. We're going to look at the time in the horizontal component and then swap that over to the vertical component. Because we don't know velocity, we're working backwards. So T, remember, D equals Vt, so T equals D over V. So that's going to give us 5 over V cos 30. So if time is 5 over V cos 30, I've got A, Vi, or Vy initial, Dy, and T. So we're actually going to use this formula here. D equals Vit plus 1/2 At squared. And we're going to come up with some cool results. So now the vertical distance this thing's traveling is 2.5 meters. That's going to equal Vi is the y direction, V sine 30 times time, which is 5 over V cos 30. Plus 1/2 negative 9.8, and my time is going to be 5 over V cos 30 squared. Looks gross, but cool results. So buckle up. Here we go. My velocities here are going to cancel first. That's nice. And we're going to start to just move stuff over right away. Because this is going to be negative. I want to add it to the other side. So we're going to get, you know what? No, I lied. I'm not going to move it over. I'm going to move just this part over because we're solving for V, and the only term that has a V is here. So this is going to stay. This is going to slide over. So we're going to get 2.5 minus 5 sine 30 over cos 30. and that's going to equal negative 4.9 times 25 over v squared cos squared theta. Oh, sorry, cos squared 30. This you could just punch into your calculator. Do that 25 or 2.5 minus 5 sine 30 over cos 30. You could use that sine 30 over cos 30 as tan 30, but whatever. This is going to, if you punch this into your calculator, it's going to give you value. Negative, actually, 0.3867. And that's going to equal negative 4.9 times 25 over v squared cos squared 30. So we're going to multiply the v squared up, we're going to divide that down, and we're going to get that v is going to equal the square root of negative 4.9 times 25 over negative 0.3867 cos squared 30. Those two negatives are going to cancel out. You run this through your calculator, you punch it in, and what you're going to get is that this thing needs a velocity of 20.55 meters per second. And maybe I should write in here, this is just notation. Sometimes there's questions about it. Cos squared 30 is just the same as cos of 30 all squared. This is just how the notation, how it gets written notationally. But there it is. How fast should you shoot a basketball? If this is what you want to do, the initial velocity should be 20.55 meters per second. You're done. Good luck. This is the last example. Got a bunch of homework questions. Actually, not a bunch. There's only 4. I want you to do 1 to 3 and 6. That's it. Again, if you have homework, or sorry, questions on the homework, please feel free to ask. I'm available today, tomorrow. There are no lessons tomorrow. Tomorrow is just a day for you to work. Hopefully, you started the review this weekend. Yeah. That was, yeah. Good luck. We'll see you later.